If I assume a periodic boundary condition, I get the blue one. So it's roughly the same. Leaving the box completely open or making it periodic has roughly the same behavior. There's another one you can do. You could say, well, you know, this outside is gallium arsenide. Well, it better take on the gallium arsenide lattice constant. So why don't I just assume the edge atoms to be on the gallium arsenide lattice constant? And I call those fixed boundary conditions in NeMo 3D. And if you do that, where you lock the atoms at the surfaces to be at the gallium arsenide boundary condition, lattice constant, you get a different behavior. It starts from the top, meaning if your box is too small and you lock and strain on the edge, you really impose a completely different strain condition on the inside of your quantum dot. And if you make it larger and larger, all these three should roughly come together. Right? Really, for an infinite system, the periodic box, the free boundary condition, or the fixed to gallium arsenide really ought to be the same. And that's what you find in this numerical simulation. So those at least make intuitive sense. Excuse me. So now you can try to be a little bit more quantitative and try to figure out what these, how far these strains reach. So we have done two experiments where we've taken a box like this. Again, we have a boundary condition where we can fixed all the way around. What we typically do, though, when we do NeMo 3D calculation, we have yet another boundary condition. It's actually a mixture of periodic, fixed, and open. So what that means is we assume on the bottom that we have a substrate, gallium arsenide. So we fix that. Then laterally we say, well, we have a periodic boundary condition because we know we're actually computing things in a pretty big sheet of things. And it's not open and it's not fixed. And we say on the top, well, we don't have really control on the top anyhow. We leave that top open. So the atoms on the top could bulge out if needed, for example. That's the typical boundary condition we use in NeMo 3D for strain calculation these days. And here's a similar experiment, but now we've, instead of making all the domains of the same size and making it bigger in all three dimensions, we've fixed a ratio between distance and height. So here we're expanding the sensitivity to distance laterally versus height. And we look at the slope of these eigenstates and look at the deeply buried dot. And we compute the difference between the mixed boundary condition and the fixed boundary condition for the electron ground state and the electron excited state. And here we see something similar where both boundary conditions tend to converge for lateral distances that are pretty big at 140 nanometers. And we do the same thing for the holes on the bottom. Now let's do a different analysis where we look and make the vertical expansion larger than the lateral expansion. What we find is that these states are converging at much smaller distances. The result between the two boundary conditions turn out to be the same for smaller lateral distances, where we expanded the height much more dramatically. That indicates that the strain is actually very much vertically oriented rather than laterally oriented. And in fact, you can find experimentally that quantum dots like to grow on top of each other. There's lots of experiments now that show where people have built quantum dot stacks and they grow on top of each other because they preferentially align themselves, which tends to minimize the overall strain in the overall system, rather than having, if you grow stacks, if you grow multiple quantum dot layers, that they don't align themselves. They actually align themselves. That is due to the vertical orientation of the strain. And intuitively, you can look at that as well, where you say, well, if you start out with gallium arsenide, and indium arsenide is a larger lattice constant, it needs to contract laterally and it expands vertically, biaxially strained. And if you grow a couple of layers, it's mostly vertical and then it clumps up. So it remains roughly vertically strained, and then in the lateral dimension you really have gallium arsenide dominating. Okay, so here is the same experiment where we look now at D and H, and D over H is fixed to 2. In this example, we have now looked at the effect of the capping layer. So we played with the distance. How far away do you need to make this baric quantum dot from the substrate boundary condition? What are the effects of the lateral dimension, and what is the effect of capping? Because those are 3 different sizes in a sense, right? Capping is something you actually could control experimentally. You might want to have a smaller cap or a larger cap if you can maybe tune your quantum dots. So here are now the eigenenergies as a function of lateral distance, and for 3 different caps. And it's not written on this slide how large A is. I have to put that on the slide. But the message here is that if you tune the cap, so if you have an 11 nanometer cap or a 17 nanometer cap or 23 nanometer cap, you can actually tune the eigenstates of your central system. Okay, so you have actually a design parameter in which you can play with tuning the energies of your quantum dots. You don't change per se the form or shape or composition anymore of the quantum dots. Actually, I take that back. You seem to change the strain in it, which might change the form and shape a little bit, but you don't change the composition anymore, right? You're not changing the number of atoms in the quantum dot or anything. But changing the strain layer on top seems to change what happens in the inside of your dot, which is a tuning, an engineering parameter. So dots, the other thing is that with the testing for B, we can sort of sense that how sensitive are we to feeling another quantum dot that is virtually sitting in our distance neighbor, okay? And these dots are coupled via strain, and only if they're very close are they coupled quantum mechanically. So the summary of this section is that strain is the source of the creation of these indium arsenide quantum dots and gallium arsenide. So it's very important for the mechanical properties of this material, of the arrangements of the atoms. It's a very long-range phenomenon. It reaches further vertically than horizontally. That means quantum dots will grow on top of each other. And electron wave functions are confined in the central quantum dots, and it can be computed in a smaller domain. Right? So strain is computed in a huge domain, and then you can chop down your simulation domain to be something smaller that is critical to the electronic structure. Are there any questions on that? Clear as mud?